nanohub.org.
Online simulation, and more for nanotechnology.
So, greetings and thank all of you for joining us today for the MassML workshop. This is a two-part workshop event, with the first part being an introductory workshop for machine learning, and the second part is a tutorial introducing the Materials Simulation Toolkit for Machine Learning, or MassML. That is a Python package designed to broaden and accelerate the use of machine learning and data science methods for materials property prediction. Our first workshop today is presented by Dr. Benjamin Afflerbach and is titled An Introduction to Machine Learning for Materials Science, a Basic Workflow for Predicting Materials Property. This workshop will introduce core concepts of machine learning through the lens of basic workflow to predict material bandgaps from their compositions. Dr. Ben Afflerbach is a research associate in material science and engineering department at the University of Wisconsin-Madison. His research uses materials informatics to supplement traditional material science research with a focus on metallic glasses.
Thank you for the introduction, Aaron. And yeah, I'll give a quick introduction before I dive in. So this is split kind of into two parts. I'll give a quick kind of PowerPoint overview, which is kind of the introduction to machine learning part. And then I'll also go through a NanoHub tool, which is a Jupyter notebook that we've used as part of a lab activity that we've incorporated here into a few courses, like Introduction to Computational Material Science course, where we sort of substitute this in as a 1 week lab in that course. And I also teach it to undergraduate researchers as part of a kind of onboarding course for new undergraduate researchers that are interested in learning about this area. So this will be a quick, hopefully kind of 10-minute presentation, and then we'll transition over to the NanoHub tool and notebook. So before I dive in, the quick summary of kind of takeaways, what I hope this introduces right at the start, and then we'll circle back to it at the end. So the key point to take away is, what is machine learning? What kind of tool is it, and what does it do? It is a tool for finding patterns in data sets. Oftentimes there are other tools out there that can do similar things, but the goal is to find these patterns, to identify them, and hopefully do this where other tools kind of fail or break down. We don't have the knowledge to sort of operate them properly. Oftentimes we use this in material science, or kind of one implementation is to substitute into these kind of material design or materials discovery workflows. And so to give an example of what I mean by that, this would be a simple kind of 4-step process here. If we identify a materials property that we're interested in this case, we'll be focusing on the band gaps of semiconductors. We want to train some sort of model that can predict the property that we're interested in, ideally from simple, accessible inputs as possible. That's often one of the ways that kind of other traditional modeling techniques kind of break down, is the inputs are really hard to get. You have to do a lot of experiments, or you have to do very detailed material simulations that take a lot of time. And then the third step would be, hopefully after you've trained and assessed your model, you can make predictions for new materials, trying to discover new things. And then hopefully you can loop back into the experiments and synthesize and verify those predictions. So that's the basic overview. That is not specific to machine learning. This, you could fit any kind of tool or any kind of model into that second step there. And I'll introduce how the machine learning loops. So here's our sample data sets and topic for today, which is predicting band gaps of semiconductors. What I'm showing here is the results from a paper in 2018 that is basically doing what we're going to do in our sample lab, but in a much more thorough way, where they are predicting machine learning, or they're giving some of the results of machine learning predictions on the y-axis here, and then comparing to known values in their data set on the x-axis. So this is a common plot, and we'll get to make some of these plots in the lab in a second, called a parity plot. And so by comparing these predictions to the known values in the data set, we have an example of all of the errors for these individual materials. So each data point being shown here is a specific materials composition. And so predictions closer to these lines in the middle would be kind of perfect predictions with low error, and then some of the points further away would be points that have high error in their predictions. And one of the key things here that isn't directly shown on this plot is that all of these predictions are coming directly from very simple, again, inputs, just elemental properties of the elements that are in this database. And we'll see how that works again in the notebook. So I mentioned a second ago this kind of 4-step basic overview of this workflow. And here shown below is kind of how we break that out for a specific machine learning model. Break that out into kind of 6 steps here. You might see this kind of grouped other ways elsewhere where you might combine or shift around things. But the way I've kind of outlined it here is first we need to generate the training data. Again, we're looking for patterns in the data, so we need enough data to identify these patterns that we're looking for. We probably need to clean that data. We need to get rid of bad data points, remove as much noise from the data as possible is kind of the overall goal, so that those patterns are as clear as possible to the model. We need to generate the inputs to the model. I mentioned earlier that simple inputs are kind of the goal in those cases. So we'll talk through feature generation kind of strategies, and we'll introduce a very common one here. And so with those 3 steps, that is sort of setting up the data and getting everything ready to go. We haven't really done anything with a machine learning model yet. And so the last 3 steps, we sort of train and assess our model. The next step after that would be, usually we would take some sort of optimization step. This is kind of changing the structure of the model to make it hopefully better at learning to recognize the patterns in our data. And then finally, once we're satisfied with the performance, we can make some predictions, and we'll get to see how that works as well. So that's the kind of overview of the structure and kind of workflow that we'll be kind of going through. Before we dive into that, I want to introduce just a few kind of key concepts and things to, again, kind of keep in mind that locate kind of what specifically we'll be doing. And the first thing, I've said this a few times so far, and I'll keep reiterating it throughout this, machine learning is all about pattern matching. To give a little bit of intuition about what we kind of mean by that, we can think of a simple kind of relationship here between atomic radius and atomic number. So I just pulled this data off of the periodic table. And interestingly, the periodic table is kind of, we can think of a very early attempt at doing what kind of machine learning is doing. It is organizing data. It is looking for these patterns within data. So if we're thinking about the data that we're showing here, and if we kind of think back to as different elements were discovered, you'd be filling in these data points. You'd be trying to find, what is the relationship between atomic radius, atomic number. If you only had maybe 10 data points on this plot, you might make the assumption that, oh, there's sort of a linear increase with atomic number. And there's probably some noise as you're going up and down. But as we kind of fill this in and we see more clearly, you can see this sawtooth pattern that's kind of coming out in the atomic radius. So these kind of discoveries, if we didn't have all the information, would be the types of things that a machine learning model would hopefully pick up on as well. So these are the kind of relationships that we're kind of talking about here. Obviously, there would be much more complex and things that are kind of harder to understand than just the relationship shown. Another kind of key distinction, or one key distinction I want to kind of make, is in what is the goal of our model. There are 2 kind of main classes of models that we can think about, and that is supervised learning versus unsupervised learning. Everything we'll be talking about will be something called supervised learning. And that is the situation where we have a set of labels or outputs for our data that we're interested in predicting. That's shown on the y-axis here. And so we can think of the goal as finding a function that represents or best reproduces that data. So that's everything we'll be talking about. There's a completely kind of other class of modeling and sort of data science techniques called unsupervised learning. And that is if we don't have those outputs. So if we didn't have the band gaps, all we had was, here's a bunch of materials data we're interested in. We want to know what are kind of the differences or what are the subgroups within this data set. So we're trying to find structure in the data without knowing what the actual properties are. And so that's something to just kind of keep in mind to sort of localize. These are terms you might kind of see if you're learning about this space. So we'll be doing everything again in supervised learning. Next kind of key distinction is to think about what kind of predictions we're actually going to make. So there are various types of machine learning models, and they can make different kinds of predictions. 2 of the key ones we'll focus on is regression versus classification. So regression is just predicting a continuous variable. Again, our band gap values would be a continuous variable we're predicting. You could also predict maybe fatigue strength or a transformation temperature, like a melting temperature. On the other hand, you could do a classification problem. So instead of predicting the band gap direct number, you could say, is this an insulator or is this a conductor? And so you're just asking your model to learn key differences between classes of materials in this case. And I've sort of set this up to kind of highlight something that oftentimes we can do this with similar data. So with our bandgap data, we could turn this into a classification problem by just creating kind of bins within our data. So if we said the bandgap is 0, that is a conductor. If the bandgap is non-zero, we could sort of loosely categorize that into insulators. And so that the choice here is related to, what is the kind of research question or the thing we're trying to answer here. And so with our bandgap data, the kind of question that we'll be trying to answer, or one of them is, is this a suitable material for like a solar cell? So we'll have kind of target bandgap that we're trying to predict. So in that case, we need these detailed regression predictions if we're going to try to meet that goal, because simply knowing something's an insulator or conductor would not be enough information to determine, is it a bandgap in this specific range. I mentioned, model types. Again, we won't be able to introduce many of these, so we're going to kind of pick one to focus on for this activity, and that is decision trees, and then they're kind of related to something called random forests. The reason we're picking these is because I think they're the easiest to kind of understand visually. We don't really have to show any mathematical equations. We can just kind of understand conceptually what's going on. So here is the structure of a decision tree. The way that these work is they kind of flow from the top to the bottom. So we'd start with this orange root node at the top, and then we kind of proceed down the tree via these connections or these branches between different nodes in the tree. So we have root nodes, we have decision nodes, which is where we're kind of splitting onto different branches. There's, by definition, 2 branches that kind of come out of each node. And then we have leaf nodes in green, which are kind of the end of the tree. And that's where predictions are made. So there's sort of a prediction assigned at each leaf node. So if we think about our data set as a whole, one way you can kind of visualize this is the data flows from the top to the bottom, and it slowly gets split out into subcategories until it lands at a leaf node. Again, you could think about it another way. If you're making one specific prediction, you can think of a single data point kind of flowing down through the tree until it lands at a leaf node. Here's a little more of a kind of detailed example. Specifically, we'll sort of show what do our inputs look like and how do we actually split at each of these nodes. So one of the inputs, or the inputs of the model, one of the terms you'll hear a lot is features. Features would be each of the types of inputs that we're putting in. You might also hear the term descriptors used around. Sometimes people use those interchangeably. I'll be sticking to just using features for the rest of the talk here. And the 2 that I've put in this sample data set is the atomic number on the left there and the melting temperature. And what we can see is we have 3 individual data points. They're elements in this case, so iron, aluminum, and carbon. And what we're showing is how each of these could then flow down through this tree and make splits at each of these nodes. So there's a single feature assigned to each node, and we're asking a simple binary question, is the feature greater than or less than a certain number? So is atomic number greater than 10 in the orange box on the left there? And then is melting temperature less than 1,000? And if we take each of these elements and kind of flow them through this tree, what we could see is that each of these land at a different leaf node. So I'll do iron specifically, just to kind of show what I mean. So iron has atomic number 26. It is greater than 10. So I'll kind of pick a convention here. I'll say if it's greater than, then we're going to the left. That's just a sort of arbitrary definition. But let's say greater than 10, it goes to the left, and it'll land at the first leaf node there on the left. And so the other 2 have atomic number less than 10, which means they would take the other split and get flowed down the other side of the tree. I'll take a quick kind of aside here to point out this is not machine learning because I have chosen the structure of this tree and I have chosen the features that are assigned to each node. This is human learning. I have designed and implemented the tree. The key thing that makes this machine learning is when we take our hands off and we say, okay, have a algorithm decide what is the structure of the tree, what are the features that should be assigned to each node, and then what are the predictions that should be made at each leaf node. So I just want to kind of make that clear here. Everything I'm showing here is just kind of a toy example to introduce the structure. And as I mentioned, each leaf node has a prediction associated with it. So here I've gone back to that sort of atomic radius example from the plot I showed before, and we said, I said, if we assign to each leaf node a single radius, we could then predict each of these elemental properties. So this is the basic structure of a decision tree. Again, I skipped over the detail of how the actual learning takes place. in the interest of time, I can circle back to that if there's questions or if there's a strong interest in that. I'll give that explanation as well. But the key thing to know is that there is an algorithm that is taking place. It is deciding each feature, where it goes to each node, what is the structure of the tree, how big should the tree be. All sorts of those decisions are kind of taking place on the back end during the training process. And again, I'll give that explanation if there's interest. So that's everything I had just for the quick introduction. Machine learning, again, it is looking for patterns in data sets. It is trying to find these relationships that are kind of hard to understand. And what we're going to try to do with it is introduce or try to complete one of these materials design. So at this point, I'll switch over to the NanoHub tool. If there are any quick questions while I'm switching over, happy to answer one or two.
I can read one out for you that we just got. Is supervised learning also known as active learning, or am I just confusing with apples and oranges?
That is a great question. I think, yes, those would be two separate things. In my mind, when I think of active learning, that would be more of implementing a process where you are, continually feeding in new data into a model and updating your model over time. That's another one of the big kind of features and benefits of these models is when you feed them more data, they continue to learn and evolve. And so, yeah, I think I would keep those separate in your mind. Supervised learning is purely related to the structure of the data that we're trying to use, whereas active learning is thinking about like a process and a strategy for training and updating your models. So yeah, that's a great question. And I agree, the terminology, there's like a lot of it. It is very confusing. And again, oftentimes people like use things interchangeably. So that is a huge like frustration, I think, for a lot of people as they're learning. Okay, so I'm sharing now my my browser, and I'll flip back to just the tool page for a second and allow everyone to kind of get on the same page here. So when you open up the tool, or when you open up the link, I think you should be on this page. Again, you will have to log in here on the top right. And then you should just be able to click this Launch Tool button, which will get you to this separate tab that I've opened here. And if there's maybe one more question, just to give people time to follow along with that, I can answer that and then dive in.
How useful are such techniques when applied to materials which do not have a sharp value for a certain property?
A sharp value for a certain property. I would say, yeah, if I'm thinking of, if I'm trying to kind of interpret that question, I think I would say, depending on, I guess, the sort of sharpness of the value, I think you know, like how sharp is like a transition maybe across something. I think there would probably be different models that would be suited to different types of data more. Like I introduced the sort of regression versus classification. So if we were doing classification, but yeah, there wasn't a sharp transition, so it was hard to make a distinction between one class and another, then it might be better or easier to train a regression version of the model where you'd predict that continuous transition, as opposed to trying to make some sort of arbitrary cutoff where you say if you're below this value, you're a certain class, you're above, you're this other class. I sort of made that kind of rough classification where I said, bandgaps 0 is conductors, bandgaps non-zero is insulators. That's not strictly true. That's just a kind of arbitrary cutoff I made. So yeah, I think in that case, if you're really interested in that transition area, then maybe looking at regression models might be better suited. So hopefully that was useful. I might have misinterpreted that. But yeah, I'll jump into the lab activity here. Again, the kind of background of this activity, I put this together originally to serve as kind of a 1-week course lab. In the supporting documents here, there's a few PowerPoint presentations, which could be useful if you're trying to sort of give the introduction, similar to how I was just giving before going through the lab activity. It's also maybe useful just as a kind of single shot example to show an example of these workflows. So once you click the Launch Tool button, you should eventually get your notebook loading up here. It'll look something like this, although the formatting will be slightly different. This first cell here will sort of change the formatting and import some kind of custom formatting to make it look like this one. Again, in the interest of time, I won't give the detailed overview of here's exactly how Jupyter notebooks work and everything like that. The quick kind of rundown is, this is interactive Python code. Each of these cells, which I'm selecting here on the left with my mouse, you can see are highlighted in orange, are either code, Python code, or they're like markdown text. And so the quick thing we can do to kind of run through this is at the top here, you can select cell and then run all. And this will just run all of the code as we go through. Or it'll pre-run all of the code, and I think get us 99% of the way through. I think I was checking this morning, and I realized I messed up something later on. So there will be one. If you're looking ahead, you might see a thing we can do to kind of run quick fix for that. So I apologize, but this will get us the way through. If you again hit run all, that will be all puts. The alternative way that you can run the code is by selecting each cell. Like here, so it's selected on the right, I'll hit Shift plus Enter, and that will run the cell and proceed to the next one. So every time you do that, you'll see the number here on the left will update, and that'll confirm that you know that cell. So anyway, I'll keep proceeding through. If there's any technical questions, I think Ryan can probably help out with those. I'll scroll down here. There's a lot of introduction, and I'll just remind us of the structure. So we have sections that are related to each of the workflow steps that I introduced before. So we have sort of data inspection, feature generation, feature engineering, setting up model evaluation, and then sort of training and evaluating the model. I've added an extra one here, which is in sort of default model, and then adding in this optimization step. And then finally at the bottom, making some predictions. You'll notice there's sort of exercises along the way. This is again, we did a group of students that might be taking this as a lab. You can work through those if you're interested on your own time, kind of skip over them. But I'll be basically going through, and my goal here is to kind of highlight the key thoughts and key things to keep in mind at each of these steps. And at the end of the day, we'll get through and hopefully have a trained optimized model that will be interesting to kind of play around with. So all of these are also hyperlinks. So I'll click on section 1, data inspection, and jump down to kind of the first section where we load in our data. So if you've, again, if above, you would hit cell and then run all. This should all have run already for you. If you didn't do that and you try to run these, you will get errors because we have skipped some cells above. So if you're following along and you're sort of skipping to here, please make sure you hit cell and then run all, or you'll probably be frustrated. So we're going to load in data sets that we have been provided. My first kind of key point and takeaway about obtaining and using data is never trust the data that you're provided. There are so many times where someone will tell you, oh, I've cleaned this data. This is good to go. Yeah, you can just use this. There's almost always going to be something that you need to kind of think about. So blindly trusting data that you're given, I think, is a big kind of no-no. So in this case, we got version 2 of the data set from our collaborator or something. And so we loaded it in and we're going to start looking at it and see if we can identify anything that we can do to improve this data set. Here's what it looks like when we just kind of output the data frame. This is a pandas data frame for those that are interested, which is a Python package. So we have one column here, which is the chemical formulas, supposedly cleaned. We have the bandgap values, also supposedly cleaned for us. We have the units for the bandgap. We have the method. This would be the experimental method used to generate the bandgaps, and then some sort of measure of reliability of this data. And the first thing that we might notice, as we kind of scan through this, if we look at kind of the first rows here, is all of these are duplicate materials. So this is a common theme in when we're doing data collection, is we will have multiple experiments that collected the same measurement for the same property of a material. So we have, in this case, it looks like 5 measurements for the same material here, and we can see that a few of them are using one method, and then a few of them are using another method. And so ideally what we want, and again, the big picture goal of data cleaning is to reduce the noise that we're kind of feeding into the model once we start training. So the goal is to look for these relationships between the chemical formula and the band gap. And so if we feed in 5 different estimates of the band gap, that is essentially just throwing noise into the model. So if there's a way that we can reduce the number of data points here for this specific material, that might reduce the amount of noise. So one thing that we do first is we look at this reliability column. And this is specific to this data set. The researcher who put this together had an estimate of which of these are the better experiments. So what we'll do is we'll say if we have reliability 1, we will trust that over the reliability 2. So the first thing we do is we kind of throw out that data, or I shouldn't say throw out, but we remove that data strategically to get the best estimates possible. So that's done a few cells down here. Again, I'm kind of skipping over some of the kind of text. This is all explained in the text as well, if you're interested in reading along. So we filter out and we only select reliability equals 1 here. And so now we have removed all the extra data where we had less reliable experiments. This didn't completely solve our problem. There's still a duplicate value here, and there's probably a few down here as well. And so there's additional strategies. I think in this case, we say, if we have no other way to kind of determine which one to trust over the other, we average across both of them. So there's an additional step that we take here. Again, in interest of time, I won't go through all the details of every single step, but the idea here is we're looking for strategies, again, to remove noisy data, to remove maybe missing data. I think I kind of skipped over that step before, but if we're missing a band gap value, we should not use that data point. Or if the chemical formula maybe doesn't look correct, maybe it's a nonsense formula, or we have some reason not to trust it, those would also be reasons to kind of remove things. But that is the kind of big picture of the idea for data cleaning, is we're trying to remove noise from the data and get to the cleanest kind of representation of each of our materials, and so that the model can learn these relationships, again, between the formula and then the band gap value that we're going to try to predict. So with that, I'll kind of skip to the next section here. For the kind of exercise questions, again, if you're interested, you can sort of look at those after the workshop. Another thing that I'll actually mention before I go on is another thing that's really useful to do at the beginning is to look at what is the structure of our data. This is just a histogram of the data set that we have after we've gone through the cleaning process. So the band gaps on the x-axis and the counts on the y-axis. And this is a very common thing, not only with materials data, but it's any kind of experimental data. It is often heavily imbalanced. And what I mean by that is this is not a flat line where we have equal representation for low band gaps versus high band gaps. This is driven by a number of things. Oftentimes, this might just be the distribution in the real world. There are just more materials with band gaps closer to 0 or 1 than there are way up here, 5, 6, 7. And that's probably true. It also might be guided by, let's say, thanks Ryan for answering questions in the chat. It also might be guided by experimental interest. Maybe all of the interesting materials are here around 0, 1, or 2. I think that's also true, where we're really interested in semiconductor design, and semiconductors are in this range. So when people go do experiments, they're only targeting the areas that they really care about. And so that's a kind of a downside for our machine learning efforts, because oftentimes we're missing data from the areas that are kind of low interest for the community. One strategy, if we had a large amount of data we could do to combat this, is we could kind of randomly subsample our data set to remove some of these points where we have almost like too much data. And sometimes you can super sample in the higher points where you kind of create sort of fake new data that is randomly nudged around the data points that you have. So you're trying to sort of increase on one side and decrease on the other side a little bit. That would all become specific to the situation that you're kind of working in, which of those might be appropriate. The thing that I'll kind of mention is we're often also limited in the amount of data we have. So I skipped over it, but if we count the total number of data points we have, I think we report here, we have 467 data points, which in the grand scheme of things is extremely few compared to many machine learning efforts where you would hope to have thousands or hundreds of thousands or like millions of data points that you're working with. If we think of things that like Google is doing, they often have millions of data points they can train on. So we're in like this very low data regime. So we often want to avoid removing data as much as possible because that's just going to reduce the amount of information we can feed into the model. So in this case, we sort of identify that we have an imbalanced data set, and we're just going to kind of keep that in mind as we kind of proceed further. It's probably going to be a limitation to the model's performance, but there's not a huge or a kind of clean solution to that right now. So now I'll skip on to the next step here, where we talk about feature generation. So I think and I think this is the point where you will need to make one small edit. And so if you're under the feature generation section here, again, this is section 2, you will probably have gotten an error, or I think definitely you will have gotten an error on this line here. So what we want to do is add a single line to our code. Basically, I forgot to define this object CWD. So CWD equals os.getCWD. That is the line we need to add in. The way that you can create a new cell here is there's this plus button up here in the top left. You can also add it to the start cell as well, just by clicking in the cell, adding that line in. And then again, to run this, you can hit Shift Enter, or maybe more easily, you can go back to the top and then just do run all again. Maybe what would be more appropriate would be to restart and run all, and that'll clear everything out to make sure we don't. So I'll do that right now. Restart and run all, and then that should get us back to where we're at. And that also sends us way to the bottom, so I'll scroll back up to where we were at a second ago. And here we go, feature generation. Okay, so here's where we started, where we left off a second ago. Something to kind of note here, so I mentioned the features that were generated here are using this software package MassML, which Ryan will be talking about during the second half of the workshop. For this lab, I pre-generated them ahead of time just to make things kind of more stable, because previously I had some issues with kind of keeping everything compatible with the current version of MassML versus kind of running here. So we kind of introduced that we can generate these with MassML. In this case, we're just going to load them in from a pre-generated feature set that we're done with that. But I'll explain the process that we used to do that, which we explain just below after we've generated them. So let me go, I'll probably go down first and then I'll come back up a second ago. And I apologize, this text is showing up very small, so let me see if I can zoom in further. So the strategy that we're using to generate the features is we are using elemental properties of each of the elements that we have in our data set. This is a kind of common strategy that's very quick and easy, and basically can happen instantaneously. We just look up elemental properties and then combine them, in this case, into composition averages for each property. So actually, maybe I'll scroll back up just to give an idea of what I mean here. So for example, we can look up the atomic number shown here for all of the elements that we have present in the data set. If I go back here, for example, we'd have this binary material at the top here. So we have 2 different elements. So we can look up each property for the elements for each row in the data set. Then we can basically get the composition average of that property. And so I show the the simple formula we use for that. Basically, with each property value, we multiply it by the proportion that it is present in the composition. So this gives us the composition average. And we can see that going through this, there are quite a few properties that we have access to using this method. These would be things that are freely available in the periodic table, other databases that are just publicly accessible. And if I scroll to the bottom of this data set, what we can see is we have generated 87 columns in our feature set. So this is 87 properties that we can use for our model. So just to, again, give an example of a few, we have the atomic number, atomic radii. Some of these are fairly simple to understand, and then some of them are a little more complex. So we kind of go over here. So this is like the magnetic moment of the material in a certain structure. We won't dig into the details of those, but the idea is all of these are giving us very simple information about the materials that are present. And most importantly, these are numerical representations and not just the previous strings that we had of the chemical formula. So we need to transform these all into numbers that we can then feed into the machine learning model. I feel like I explained that really poorly, and so I apologize if that was confusing. If there are questions, I think Ryan can maybe help out and explain as well, and I'll can also circle back at the end and maybe explain that better. But the idea is that we are generating this feature data frame, and this is going to be the actual inputs that go into the machine learning model. So again, we have a few exercises kind of asking about that. And the other thing that or the next thing that we want to do is this separate step that I've kind of pulled out here, which we're calling feature engineering. Once we've generated our feature set, or sometimes depending on the data, it will come with features already and we don't have to generate them ourselves. But there's often a step where we want to manipulate the features somehow. Again, the end goal is to make the features as easy to understand. Relationships between the features and the thing we're trying to predict is easy to make as possible. There are a few common things that we would do. We introduced 3 of these here in the notebook. First, we remove constant features. Again, if we're looking for relationships between input features and the output target variable, if we have constant values, there's no way to learn that relationship. So this is just of no help to us. So removing it is fairly trivial. The other thing, which is a little more maybe sophisticated and interesting to look at, is removing highly correlated features. In this case, I think I use the term removing the columns. Again, the columns are the features in this data set. So I'll show what that kind of section of the code here looks like. We can visualize the correlation by making a correlation plot here. This is looking at the Pearson correlation number in this case. So we have the features just identified by their number here. Again, we had 87 total. So you can see it goes up to 80 plus a little bit. And the darkness of the color here is how highly correlated these are. So we have this diagonal line because each feature is perfectly correlated with itself. And then you see there's some pockets in here of really high correlation between some of the features. The reason we might want to remove these is because, again, the goal is to have a set of features that provides information to the model where it can learn these relationships between the outputs we're trying to predict. If we're feeding in perfectly correlated features, you're basically feeding in the same information twice or slightly varied information, which is less likely to provide kind of useful information or new information to the model. So in the sense of trying to provide kind of the smallest feature set possible that has the highest kind of variability of information, we can remove these highly correlated features. So we go from 80, and then I think we remake the plot after going through that process here, and we remove down to 71 or 72 here. And we can see a lot of these pockets of high correlation and provide unique information to the model. That's kind of the goal here. So again, the key message and the key idea behind feature engineering and sort of modifying our features. This can be a little bit strange, I think, to people at the start because it sort of feels like you're just sort of arbitrarily manipulating your features and like you changing your input data. And from a kind of experimentalist point of view, that feels very strange because you're taught we collect the data and then we can't just arbitrarily throw things out, or we can't just change our data around. And so it's important to keep in mind, like, what are the motivations for doing each of these steps? We're doing all of this ahead of time before we've seen any outputs. So we're definitely not like doing this to specifically make our model, behave a certain way or something like that. We're doing these for like fundamental reasons to improve the quality of the data. The last kind of method here that we introduce is feature normalization. This is where we rescale the features so that they are of similar kind of magnitude to each other. A common thing that happens in some model types is if you have one feature that say ranges between 1 and 100 and another feature that ranges between 0 and 1, the feature that goes from 0 to 100 has much more dynamic range to it. It also has a larger magnitude overall. Oftentimes that will kind of dominate the training process of the model just because it's larger and kind of the math works out that a larger variability there, sort of helps it dominate the training process. So even if a feature between 0 and 1 was super useful, it might just get ignored during the optimization process, or during the training process, I should say. So this is a way to kind of put all the features on the same playing field. It kind of rescales them so that they are similar. They are of similar magnitude and similar dynamic range. I won't go into the details of that, again, in the interest of time, because I realize I think I'm a little bit behind. So I'll go on to the next step here. So everything we've done so far is basically, how do we set up our data? How do we get data and generate the features and make sure that they're as good as possible? And so the next step here is now when we talk about how do we set up and evaluate a model and train a model. And so the key thing that I'll point out here, there's kind of a lot of content in this section. But the key thing that I think at the base level is important to identify is the importance of splitting our data into a training set and a testing set. So maybe I'll just show right here rather than the code itself. We have generated a data set that is all of our X values, all of our features, and all of our Y values, which is our labels or our outputs. And if we just trained a model on all of the data at once and then predicted all of the data again, there is a concern that the model would overfit to the data. It would learn the relationships, again, between the inputs and outputs very well, but it would not translate well to new data that it hasn't seen before. It would become so tightly fit to the specific data that's been shown that anytime you gave it new data, it would extrapolate basically wildly, and we would have no way to understand that. So by splitting our data into different sets here, we can train on one set of data and then test how the model performs on data that it hasn't seen before. When we can make that test, that then gives us an approximation of how is this model going to perform on new data that it hasn't seen. So a common way that we do that is we just generate a random subset of the data. So in this case, we identify the test fraction of the data is going to be 10% or 0.1, and we generate a random split of the data. And we can visualize that in the plots here. So I make this histogram plot that we made again at the beginning, and shown on the top is the training set, and on the bottom is the test set. Again, I pointed out before, we're kind of in a very low amount of data regime. So when we do this, we can see that this test set is not perfectly mirroring the training set. So some of these values are missing, especially at the higher end, we're kind of missing some bandgap values. And this is important just to realize as a kind of limitation of being in this small data regime is when we start pulling out data from the training set to use for testing data, it is going to have some limitations associated with it. We could pull out more data to try to fill in these gaps, but then we'd have less data to train on, even less data than we already have. So we had 460 data points, I think, or so. We pulled out 10%. So there's 46 data points here, and as we keep adding more to the test set, that means we have to remove more from training, which is going to reduce the model's performance. So again, this is a kind of limitation to kind of recognize, and there's a kind of trade-off here between how much data you're leaving out for testing versus how much you're using for training. And we'll get to see kind of evidence. I mentioned this idea of like overfitting of the model. We'll get to see evidence of that once we start actually training our model. So we do that in the next section. We fit and evaluate a default model. We've set up a training set, we've set up a testing set, and basically now we want to train our decision tree model. We set this up through a few lines of code. You might notice here, and it might be confusing, we use the random forest structure here in one of these Python packages, but we're going to set it to have a single tree, which makes it kind of the equivalent of a decision tree model. We do that just for ease of use for a later section. So if you're looking at the code and you're like, this isn't a decision tree, you might kind of see that. So we go through the kind of training process. If you want to see, where does training actually take place, it is basically on this single line of code. So we say, here's our model. We feed in some information about the structure of the model and different inputs. And we basically use this one method here, fit, and we feed in the training data for X's and Y's. So Fundamentally, like doing the training is very quick and easy. If I rerun this cell, it trains basically instantly because one, we have a low amount of data, and also we have a very kind of simple model overall. That's kind of where that actually training takes place. Model training complete, and then we can visualize our outputs in one of the later sections here, which I'll show here. So I mentioned before, again, we split our data. We have a training data set, we have a test data set, and what we're showing here is a parity plot of what the model's predictions look like. This is functionally the same plot that I showed at the beginning of the PowerPoint slides, just with a slightly different data set. So we have our predicted band gaps on the y-axis, we have our measured band gaps on the x-axis, and what we can see when we reproduce the training data, this is the data the model has already seen before. The model is perfect. It has errors of 0. Everything is perfect. We generate a few statistics here, which I won't have time to kind of define, but the error here for training data is functionally 0. However, when we look at our test data on the right-hand side, it is most certainly not 0. And what we can see that are extremely poorly predicted. Some of the errors here, if we look at kind of the number here, it has an average root mean squared error in this case of 1.2. And there's notable outliers that are underpredicted and overpredicted. So this is evidence that the model is overfit to the training data. It has learned all of the information here perfectly on the left, but then when we try to extrapolate with the model, it can't. It actually hasn't learned any of the relationships. It's just learned how to produce a specific data set. And this is one of the reasons we, again, do this training and testing split is so we can identify this problem. So we know that the model is overfitting to the data. One way that we can combat that is by changing the structure of the model. So we presented this idea of making a single decision tree, and one kind of change to the structure is we can just make multiple decision tree models and put them into a structure called a random forest. So we make a bunch of random decision trees, and then we average across them to get a single prediction, which oftentimes can combat this overfitting issue. So that's the next thing we do. And again, I'll skip to kind of the next section here to show what that looks like. Actually, it might be useful just to do a quick show and tell of like what these decision trees look like. So let me scroll down until I find a cell here. So there's this output here. This does get very big if you see in your own notebook, but hopefully you can scroll around and kind of find here. But here's a few of the decision nodes within the tree. I just thought it'd be useful to show this really quick. So this is what the machine learning model has learned and what it's trying to put at each of these nodes. So it's looking at the boiling temperature in this case. Again, the composition average. It's making this split based on a certain value, 0.291. It's giving us the error at this specific node, what the value is, or sorry, what the predicted value would be if this was a leaf node, and then how many data points are kind of flowing through this node. So there's 12 data points coming through here. So you can kind of look through that. That might be interesting to look at later as well. You can expand and contract that by clicking on the left like I just did there. So you can make it a little bit smaller. And so, yeah, I mentioned we trained our default model. The next thing we might want to do is optimize the model hyperparameters, or sort of the structure of the model is another way to think about that. Looking at the time, it looks like I don't have a huge amount of time to kind of go through too many details here. But the key thing maybe I'll point out, again, is that we have these hyperparameters of the models. These are defined in whatever software we're using, and you can change their values, which affect how the model learns. In this case, we're changing one of these values, which is just the number of trees in the model. So we're building more or less decision trees. So we can reproduce the whole process that we just did before, changing this value. You can see I list a few of the other ones here just for example. But here we set, here's the different number of trees that we're going to try. And we basically just build a quick workflow where we build a number of different models. We assess them using the same training and testing data, and we look at how they're performing. So that's all happening in these cells here. And we output that, if I scroll down here, with this plot here. So this is a learning curve of how the model learns related to the different number of trees. So we have a certain error metric that we've pulled out here. This is just a numerical representation of the parity plot data that we had above. And what we can see is that the model, as we increase the number of trees, these errors, start to decrease. And most importantly, the validation or the test data decreases here. So the orange points, decrease down from being quite high down to a much more reasonable value. So what this is kind of telling us is that if we increase the number of trees, hopefully this overfitting problem will reduce or go away. And so we try to kind of look in more detail to see if that's the case by looking at our optimized model. If I scroll down here, I'm just going to go find the parity plots here just to compare. So now if we look at just the training data, so this is training data for the default model on the left and training data for the optimized model on the right, we can see we've actually decreased, it looks like, the performance of the model. The training data is not fit as tightly to this line here. Again, this is might intuitively look like, oh, we've lost performance, but the training data isn't what we really care about. What we care about is the test data. So if we scroll down to the test data here, now the default model again is on the left and the optimized model is on the right. So previously we have these huge outlier points on the left parity plot here, whereas on the right, things have tightened in significantly. So by sort of sacrificing some of the training model performance, which again, we don't really care about, we've improved significantly the performance on the test data. So now the model that is optimized on the right will extrapolate much more closely to the data that it hasn't seen before. And again, we can sort of express this numerically through some error metrics. But this is kind of the process that we would go through to optimize a model. Wrapping up the previous section, I was talking about the parity plots for the optimized models. So the goal here and the sort of evidence of success of this optimization is seeing the test parity plot where all of the error and the data points have gotten much closer to this ideal dashed line down the middle. So all the predictions are much closer to the measurements. And so the last section we have, making predictions. Maybe one thing I'll kind of point out here, which is I think the key kind of takeaway is that even though this comes right at the end, this is oftentimes the place that we would start if we were thinking about a new project. As I mentioned before, the model types that we use, the type of assessment that we use, the predictions that we want to make are all going to be related to this last step of like, what is the end use goal of this model? In this case, we identify a few here in the lab. And in interest of time, it looks like I don't really have time to go through those. One of them, as I mentioned before, was just predicting band gaps that would be appropriate for solar materials. And so maybe I'll leave to your own interest to kind of look through how the model actually performed. Did it succeed in identifying any new solar materials? And then there's one other task that we identified. But the kind of takeaway here is this all should loop back into the sort of design of the data and the design of the assessment and all the other steps that we've done before. So yeah, with that, I think I'll wrap up. And hopefully I have time for maybe one or two questions. Yeah, so that's a really good question I'm seeing in chat from Jean Castillo. So yeah, the question is it worth feeding in structural information to the model? And that is yes, like definitively yes. Any more information we can give is only going to help things. So one of the main limitations to the kind of feature generation method that I introduced is it only knows information about the elements that are present and in what quantities. So if you have different structures of materials, two chemically identical materials with different structures, that representation of your data is not going to see that. There will be no features that are functionally different between those two. So the model is going to think they're the same, even though the structure is different. So yeah, that's something to be like I'd say a big limitation to just that one feature generation method. So that's a really good insight.
How can we predict if the band gap is direct or indirect?
That is another great question. The answer for this data set would be we cannot. Our input data has no information for us about direct versus indirect band gaps. So in the case of this specific example, it would be like we have no idea, unless we dug into the source of the data and maybe we found like, oh, all of these are direct or all of these are indirect or something like that. The way that we would be able to do that. If I was thinking like more holistically, if we had infinite access to data, we would need first data that is labeled between the two. So you would need a second or additional column that tells you that you could train on. And then you might layer a classification model on top of the regression model that then makes that classification prediction versus direct and indirect. So it would be sort of a data set issue right now based on what we have. And then there's maybe a more complex, sort of layering of models where you might make a regression model and then, combine it with a classification model. And sometimes those sort of strategies are referred to generally as kind of transfer learning would be kind of a keyword to look up if that was something of interest. So you can kind of use the outputs of the regression model then as inputs for the classification model that's taking the bandgap prediction and then trying to split it into two classes.
All right, thank you so much, Ben.